Welcome. We are looking at analytical solutions to the diffusion equation. So, yesterday we saw one solution in the last lecture we saw one solution where we had a sinusoidal variation and the time dependent part was exponentially decaying. We found that solution by using variable separable method, and we basically reduced the given PDE, which is the diffusion equation, to two ODEs, and we solve them one after another, and putting the solutions together we obtained that solution. This is a solution which we also use to discuss what happens to the classical diffusion equation when the diffusivity becomes negative. Now, I want to show another solution which is also very commonly seen, but the derivation of this solution is not typically shown, and I am going to try and derive this solution which is known as the error function solution, and let us derive this solution. And for doing that, I am going to again non-dimensionalize the diffusion equation. The reason why I am doing it for the second time is that this non-dimensionalization is slightly different from what we did earlier. That is one reason. The second reason is if I do more than once, it will become much more clearer to you. And the error function solution is also obtained under some boundary conditions. So, we will also have a discussion on what type of boundary conditions we use in deriving this solution. So, the equation that we are trying to solve is the diffusion equation. So, the rate of change of concentration is dependent on the curvature of the concentration with respect to the position. The condition for which we are trying to solve this equation is as follows. So, I have so this is the domain and this goes up to infinity, okay. And so this is the x, and that x and the rod continues, and at position this x equal to 0, I am going to have a concentration of C0. Rest of the domain has a concentration Ci. Okay. This C0 and Ci could be very small numbers, right. C0 could be some 0.02 for example, and the Ci could be some parts per million for example. So, we want to non-dimensionalize. This is the reason why this non-dimensionalization that I am going to carry out is slightly different from what we did earlier. So, I am going to first define a parameter eta, which is defined as follows. The C at any point minus Ci divided by C0 minus Ci, right. This is C0, this is Ci, and C0 minus Ci is basically the difference. So, I am going to normalize everything by that. So, you can see the advantage of doing this is that at x equal to 0, when C is C0, eta is going to become 1, and everywhere else where it is Ci, eta is going to become 0. So, eta is a variable that now runs between 0 and 1, right. The range of eta becomes 0 and 1, right. It could be equal to 0, equal to 1, but anywhere in between it will be between 0 and 1. And of course, we are going to non-dimensionalize. So, I am going to choose a time t naught as the characteristic time, but for now I am not going to tell what that t naught is. Okay. We will choose it later in such a way that some non-dimensional quantity becomes unity. So, t0 is the characteristic time, and let us say that this rod, which is very large, right, nothing physically is infinite, mathematically it could be infinite. So, we are going to choose L as the characteristic length, and this L happens to be the length of this rod, and the diffusion distances over which we are going to look at diffusion, that is the normalized. So, x divided by L, that I will call as Z, and t divided by t naught, that I will call as tau. Okay. So, this the x over which we are trying to look at diffusion, compared to that the L is very large, so that is going to be a small number. Okay. But L is a characteristic length, typically it is the length of the domain itself. Now, if we put it here, we get dou eta by dou t is equal to d t naught. So, dou eta by dou tau d t naught by L squared del squared eta by del z squared. Okay, so, this is my non-dimensional equation. So, it differs from the earlier non-dimensionalization in it that we did not non-dimensionalize or scale C. Okay, even if it is a number, this scaling is still useful because this makes the variable go from 0 to 1. Whereas, if you just take concentration, concentration could be anything. So, for example, this C naught could be 0.02 and C I could be some parts per billion or parts per million. So, these kind of small numbers we do not want to deal with. So, concentration itself is going to be between 0 and 1, but it could be quite close to 0, or one number could be, for example, this could be like 1 and then that could be like 0.01. So, that is still about 100 difference in order. So, we do not want to do that. So, we are going to scale it in such a way it goes between 0 and 1, and this is the non-dimensional equation that we have obtained. Now, I am going to choose the characteristic time in such a way that d t naught by L squared becomes unity. So, that is how I choose the characteristic time. So, what does that mean? So, I want to choose t naught to be L squared by d. What does that mean? So, you have some particular length and square the length, divide by the diffusivity. So, that will give me the time that is probably it will take for the diffusion to happen over that entire length, given that this is the diffusivity. So, that is the t naught that we are going to choose. If so, then what happens to d t naught by L squared? That becomes unity. So, our non-dimensional equation now becomes dou eta by dou tau is equal to del squared eta by del z squared. Okay. And we know that eta equal to 0 at tau equal to 0 for 0 less than z less than 1, right. So, this is the initial condition, because at time t equal to 0, we are going to have this eta to be 0 everywhere, and then eta becomes 1 at all tau greater than 0 for z equal to 0. Okay. So, here it is 0 greater than z less than or equal to 1, we are excluding 0 because at that point we are always going to have a concentration. Okay. So, this is the boundary condition. You might think that there is only one initial condition now, right, because at time t equal to 0 I am telling you what eta is, and I am telling one boundary condition for time greater than 0 at one point what happens. What happens to the other boundary condition? What happened to the other end? That condition is already there, okay. That is not included explicitly because we are considering a system which is infinite, right. We are only worried about x equal to 0 and what happens to the diffusion. As far as we are concerned, the rod is extending to infinity, that is the time scales that we are going to consider for looking at this solution. The concentration still is going to remain at Ci at the extreme, okay, far away from this point where we are looking at diffusion, the concentration remains at Ci throughout. So, that is the reason why that other boundary condition is missing. So, this solution, error function solution, is meant for, as they call, some semi-infinite rod, right. So, you have a point, the origin x equal to 0 or z equal to 0, but the length is so large and the z for which we are looking for solutions is much smaller compared to L. Okay, so x by L, which is the z for which we are looking for solutions, is much smaller. So that is the condition under which we are looking at diffusion. So we always assume, though even though it is not explicitly put here, that eta remains at 0 far away from this point. So we have this where it is eta equal to 1, and then this rod, it continues and there is no end to it, and that end wherever it is, eta remains 0. So that is the other boundary condition, and that is why you do not see it explicitly mentioned here. So we have now an equation which is non-dimensionalized and which has a scaled composition variable. We want to find a solution for this problem. The assumption that we are going to make, or the way we are going to derive this solution, is to say that this solution for concentration eta is going to be like this. I am going to assume that eta is only a function of z divided by root tau. Okay. Please remember, we have assumed all of this as non-dimensional. So, this is just a number. Dimensionally speaking, if you are having length as x, then square root of dt is what will become non-dimensional. Okay. So, because we have assumed this non-dimensional d to be 1, that is why it is not appearing, otherwise there is 1 here which is standing for the diffusivity. Okay. Now, why is this true? This is sometimes argued as follows. So, in the diffusion equation, so let us take the diffusion equation. Only dimensional quantities are length and time, and diffusivity has derived units. So, if you try to form a non-dimensional number from these quantities, that is of the type x squared by dt, right, because this is meter square per second and multiply by time. So, it will become meter square will cancel. So, this is some non-dimensional number, right. This is some non-dimensional quantity, right. As x and t change, this quantity value can change, but it does not have any dimensions. Okay. For a given diffusivity, this quantity is a non-dimensional quantity. So, what we are saying basically when we are assuming that eta is only a function of this quantity, is to say that any solution for this equation will have only this quantity, because I mean if you try to take the non-dimensional version of this equation, then this is the only non-dimensional quantity that you can make. So, the solution should be in this form, and this is nothing but square root of this quantity, right. So, x divided by root dt will also be non-dimensional, and this is what is being taken here, z by square root of tau, which is the quantity. This quantity is very important, by the way. So, this x squared, which is equal to root dt, is known as the diffusion distance. Okay. And it is a very quick way of estimating how much diffusion will take place in a given time given a diffusivity. Suppose you want to throw something in a furnace and you want to know how long should you keep it in the furnace at that temperature for some amount of diffusion to take place. If you know the diffusivity, just multiply by the time that you want to keep it and take the square root, that will be the distance over which diffusion will take place in that particular time. Now, this is a very quick way of estimating it. This is the answer will be scaled, will be a factor of this distance, but this is a very good first approximation for diffusion. There are exercise problems, probably we can have some tutorial problem where you can actually estimate it using x is root dt, x squared is equal to dt. So, you can estimate this quantity and you can actually take the analytical solution, so say let us say error function based solution, and you can compare it, and you will see that most of the times this predicts very nicely for most practical purposes. Okay. And because there is also the analog, there is a common exercise that I like to always give students, that you can take a ceramic material for example, and you can take its thermal diffusivity, and you can take a metallic material for example, and you can take its thermal diffusivity, and you can assume that a cup made up of this ceramic material and a cup made up of this metallic material, metal or alloy, let us say that they have the same thickness, okay. And now you pour coffee in them, coffee which is at say some 80 degrees Celsius, and you can hold the ceramic cup longer than you can hold the metallic cup, because the distance over which you will start feeling the heat, or the heat conduction takes place and the temperature rises, right, for the same thickness. You can assume that both of them for example 3 millimeter thick, but 3 millimeter thick metal, how long will it take for you to start feeling the temperature on the outer wall if you pour hot coffee in the cup, and 3 millimeter thick ceramic, you can compare. And basically it is the difference in thermal diffusivity in the two types of materials which decides that metallic material within a few seconds you will start feeling, so you can't hold the cup, whereas in ceramic material it is at least one order higher, so maybe about a minute or so you will be able to hold. So that is why it is preferable to drink coffee in ceramic cups. It's always preferable to drink coffee, and it's preferable to drink it in ceramic cups, okay. So this is an important quantity called the diffusion distance, and here we are using some dimensional arguments to say why the solution should be of this type. Please remember, our aim is to take a PDE, somehow convert it into a ODE, because ODE is all we know how to solve. So one way of converting into ODE is by variable separable method, which we saw in the last lecture. And this lecture we are going to see how to get a ODE from the PDE, that is by using dimensional arguments. You say that there are two fundamental quantities and one derived quantity, let us make a non-dimensional number out of it, and that non-dimensional quantity is called diffusion distance, x squared by dt, and the solution should be a function of this quantity, that is what we are claiming, which is what going to help us to make a ODE out of this PDE. So we will start from this point. So we will take eta to be just a function of z by root tau, and we are going to convert the diffusion equation, not in this form. So the non-dimensionalized diffusion equation, okay. Using this, we are going to convert this into an ordinary differential equation. So which is what we will do in the next part of this lecture. Thank you.